kickstart our tour on Bernoulli's equation, let's start with a very simple example. A simple application of Bernoulli's equation. Now, as you have known that Bernoulli's equation written is pressure plus with half rho v squared plus with rho g z is equals to a constant c. So let's just have a quick talk about this. Now, what we can do is that for the z, we need to define a reference point. And the reference point is also called the reference datum. Basically, it's at a point where the height is equal to 0, z equals to 0. It can be any point, an arbitrary point, because when we equate the two, they're going to be the same. Now, next thing is that we need to be aware of the assumptions where we apply this version of Bernoulli's equation. Now, like I said, there's also a lot of different versions, one of which we can just simply differentiate that and get like another version. However, these are the assumptions that we have made when you use this equation. That is, there's no shearing stress. Notice that there's no tau value, so there's no shearing stress. Density is a constant. So remember, we were able to do the integration because density was a constant. So basically the fluid is incompressible. And the other thing is that we are assuming a steady flow. So we have to bear that in mind. I also would like to add that Bernoulli's equation is a form of the conservation of mechanical energy. So we need to keep in mind that there is no somehow like external forces that is added or subtracted from the equation. But this is a direct application. Now there's a lot of ways that you can analyze it, but one of the more rigorous way, or like I always like things to be rigorous, is to draw a streamline from a certain point, but all in the liquid, and there is no external force. So there we're going to use an example to see that, and that is basically the siphoning device. So if you have water over here, you put a tube, sometimes the water will go out of the tube, like this I have right here. And we're just going to use Bernoulli's equation to analyze it. So what we're going to start out with is that we start at point A. Now there's point A dash, B, and point C. So we'll just start our streamline from point A. It goes around here, knowing that you don't need to draw it straight. You can just draw it curve or whatever. Okay, and it goes to point A, it goes all the way into the tube and all the way to point C and out of the tube. So that is our streamline. To be more precise, the streamline needs to start and end at a point. So that's the point that we end, and that's the point that we started. So that is our streamline, and we can apply Bernoulli's equation to this whole streamline over here. So what we're going to first start is that we want to find Vc, the velocity at point C, knowing that this is atmospheric pressure. So we'll just write this equation. Why don't we do at point A first? So the left hand side will be point A. So the pressure atmosphere plus this will be half rho, and we got the V squared, but let's just put as VA for now. We don't know what it is. The rho is inside, so we got rho. Now, what is Z? Well, basically, we need to define our datum, right? Well, for convenience sake, let's define the lowest point as our datum. So that will be point C. So the reference datum, DATUM, is Z equals to 0 at point C. That will mean that for point A, Z will now be equals to 2.4. No surprise about that. Now we write equal sign, so let's just apply Bernoulli's equation to the other side immediately. You have pressure atmosphere plus with half rho Vc squared, which is what we want to find, and we got plus 0 because the datum is 0 at point C, or the potential gravity 0. So that's our equation that we have. Now, it wouldn't take long for you to see that we can cancel out the pressure and atmosphere. Let's have a small little argument. Well, basically, this at point A, this part is open to is the free surface, open to the air. So that's the pressure, is the atmospheric pressure that acts on point A, written over here. At point C, it's also atmospheric pressure that acts on point C, because, like I said, the tube is open to the air. That's why it's atmospheric pressure. That's why we can subtract and cancel out the two terms. Okay, now next, what do we have? We can cancel out the density, correct? Yep, we can cancel out the density. And so we are left with the velocity. Now here is where things get a little bit tricky. Or how should I say, in an engineering point of view, we need to place certain assumptions that will seem logical. What is the assumption that we have here? The assumption that we have that Vc is much greater than Va. If you think about it, Va is a big tank, or at least the surface area is a very big tank. And for V, and the tube is very small. So what I can say is that the velocity that is moving in the tube is very fast, but compared to the velocity at point A, which is the big tank, the velocity is very slow because the tube is very small and the water can't be moving at such a great speed such that it changes the structure or the system at point A. So knowing that Vc is much greater than Va, we can just immediately write Va is approximately equals to 0. Now you siphon some water, you don't tell me that you see water at the surface moving at such a rapid pace. It doesn't. Okay, so with this assumption, and this I would just like to say from an engineering standpoint, okay, just take it as an engineering standpoint. this would equal to 0. So basically we can cancel out this, and now our equation becomes VC squared is equals to 2G 2.4 times 2.4, and this one VC is now equals to 6.06 meters per second. 6.86, sorry, 8.68, so we got VC is equals to 6.86. There we go. A simple application of Bernoulli's equation, drawing a streamline, analyzing, and making certain assumptions. Remember, this is critical in solving problems. You need to make certain assumptions. Now, we got our velocity at point C, but we're not done yet, because what we want to find is that we want to find the pressure, or shall I say the pressure difference at point A dash and point B. What we will do is that we will now apply Bernoulli's equation at point A dash and point C, because we found the velocity at point C. I would also like to re-emphasize that notice that even though point A dash and point A are on the same level, the pressure is not the same. It does not follow a hydrostatic distribution. Why? Because remember, hydrostatic distribution of pressure is only applicable when the fluid is at rest. Well, certainly now the fluid is moving at point A dash, so it's not at rest. It does not follow hydrostatic distribution. Do not make that mistake. That's why Bernoulli's equation, we can relate A dash and C. Let's just apply the equation. So the pressure at A dash plus with half rho VA squared. Let's just keep the VA squared there, plus with rho G and the distance from the datum, which is 2.4. And it's going to be equals to the pressure at C, which we will just write as P atmosphere, plus with half rho VC squared and plus with 0. So what can we say now? Notice that the velocity at point A dash is going to be equals to the velocity at point C, as in the inflow of the liquid over here is going to be the same as the outflow of liquid over here via the continuity equation, which I don't have it with me right now, but logically speaking, it does make sense. It's also a re-representation of the conservation of mass. The liquid that goes inside here has to be the liquid that goes out. So if we can see that this value and this value is going to be eliminated altogether, and what we can right now write is that PA, take away P atmosphere, is going to be equals to minus 23.5 kilopascals. Do not be intimidated by the minus sign, because we're just basically taking the difference with the P atmosphere. We don't know what the P atmosphere is, so that's why we'll just write it like that. The next thing is that we'll do the same calculation for B, and I can just simply write it down as this now changes to 3.6, because we are going from here all the way to point B, 3.6. Again, by a continuity equation, the velocity here and the velocity here is the same, so we can eliminate these two, and I'll just immediately write as the pressure at B subtract with the pressure at atmosphere is going to be equals to 35.3 kilopascals. Again, minus sign, but doesn't matter, because what does this equation tell us? Observing it carefully, notice that the pressure at A dash, is going to be more than the pressure at B. That means when we subtract the same value, we got a less negative value. So this one is going to be more than this, if I write it like that. And this explains the siphoning effect. Because it's the higher pressure that is able to move the liquid all the way to point B, after which the effects of gravity will move the liquid down. And there we go, application of Bernoulli's equation, drawing a streamline, analyzing the points, applying the equation, and hope you would stay tuned for the more examples, more difficult examples coming up. Thanks, Bernoulli here.